Welcome back, fellow mitochondriacs, to another episode of Cancer as a Mitochondrial Metabolic Disease. Most of us are taught that oxidative stress is dangerous and that antioxidants protect our cells. But in cancer therapy, the strategy is often the exact opposite, increasing oxidative stress to push cancer cells beyond their limits. The reason lies with the fact that cancer cells walk a metabolic tightrope. They already live and even thrive under high oxidative stress, and some therapies work by pushing them over the edge until they crack under the pressure. Today, we're going to introduce oxidative therapies for cancer from a mechanistic perspective. So without further ado, let's get into it. So far in this series, we have introduced redox biology, biochemistry. We have gone over in great detail how cancer cells maintain their redox homeostasis. And we even did a little detour into probably why antioxidants are not a good idea if you have cancer. But we're going to finally get into what oxidative therapies actually are. And then we're going to dive deep into specific oxidative therapies so that we can actually go over how they work, what they do, etc. So for this video, I'm going to be mostly using this paper that was published in November of 2020 and is titled Oxidative Stress Inducing Anti-Cancer Therapies, taking a closer look at their immunomodulating effects. And it says here in the abstract, cancer cells are characterized by high levels of reactive oxygen species, ROS, compared to normal cells as a result of an imbalance between oxidants and antioxidants. However, cancer cells maintain their redox balance due to their high antioxidant capacity. Recently, a high level of oxidative stress is considered a novel target for anti-cancer therapy. This can be induced by increasing exogenous ROS, reactive oxygen species, and/or inhibiting the endogenous protective antioxidant systems. Additionally, the immune system has been shown to be a significant ally in the fight against cancer. Since ROS levels are important to modulate the anti-tumor immune response, it is essential to consider the effects of oxidative stress-inducing treatments on this response. In this review, we provide an overview of the mechanistic cellular responses of cancer cells towards exogenous and endogenous ROS-inducing treatments, as well as the indirect and direct anti-tumor immune effects, which can be both immunostimulatory and/or immunosuppressive. For future perspectives, there is a clear need for comprehensive investigations of different oxidative stress-inducing treatment strategies and their specific immunomodulating effects, since the effects cannot be generalized over different treatment modalities. It is essential to elucidate all of these underlying immune effects to make oxidative stress-inducing treatments effective anti-cancer therapy. And if we were to look at just the overview of what this paper is trying to show, it's going to be basically twofold. It's going to be looking at exogenous ROS inducers, and it's going to be looking at endogenous ROS inducers, and/or lastly, how to affect the antioxidant systems to reduce the ability for these cancer cells to maintain homeostasis with oxidants and antioxidants. In the introduction, it says, reactive oxygen species, ROS, is a collective term referring to unstable, reactive, partially reduced oxygen derivatives that are produced during metabolic processes within the mitochondria, peroxisomes, and the endoplasmic reticulum, ER. A subset of ROS is also continuously generated by enzymatic reactions, including cyclooxygenases, nicotinamide adenine dinucleotide phosphate, NADPH, oxidases, NOx, xanthine oxidases, lipogenesis, and through the iron catalyzed Fenton reaction. Examples of ROS include hydrogen peroxide, superoxide anion, singlet oxygen, and the hydroxyl radical. Tight regulation of these ROS levels is crucial for cellular life. Therefore, cells benefit from a complex scavenging system based on different antioxidants, including superoxide dismutase, SOD, glutathione, GSH, peroxidase, peroxyredoxin, thioredoxin, and catalase. Additionally, to the strong antioxidant activity of the before-mentioned enzymes, various non-enzymatic small molecule antioxidants such as glutathione, ascorbic acid, vitamin E, polyphenolic compounds act as scavengers for different types of ROS. Cancer cells are characterized by increased production of ROS compared to normal cells. The persistent high level of ROS can be explained by the imbalance between oxidants and antioxidants in cancer cells and the ongoing aerobic glycolysis, aka the Warburg effect, or cytosolic substrate level phosphorylation by pyruvate oxidation in the mitochondria, also known as the Warburg effect. This is a consequence of hypoxia in the tumor microenvironment, TME, resulting from the imbalance between oxygen supply and consumption due to uncontrollable cell proliferation, ultrametabolism, and abnormal tumor blood vessel growth. Cancer cells evolved mechanisms to protect themselves from this intrinsic oxidative stress and developed adaptation mechanism by upregulation of pro-survival molecules and their antioxidant defense system to maintain the redox balance. For instance, nuclear factor erythroid 2 related factor 2, NRF2, which is a transcription factor in the first line of antioxidant defense against oxidative stress, is often upregulated in cancer cells and supports cancer cell proliferation. So let's just stop here for a second. NRF2, this is a compound that upregulates our endogenous antioxidant responses. And in most contexts, we consider NRF2 a good thing, but it's overexpressed in these cancer cells, and they have extra antioxidant defenses that help protect against oxidative stress, not only in their internal environment, but any induced oxidative stress that's induced by either chemotherapy or radiotherapy from a conventional perspective. This is a major reason why giving antioxidants like vitamin C or CoQ10 or NAC, or in the last video that I took heat for, likely most doses of normal astaxanthin is going to shoot us in the foot because it's going to support either NRF2 upregulation and antioxidant defenses, or they're going to act directly as antioxidants, which help protect the cancer cells and allow them to support cancer cell proliferation and growth. A low to moderate increase in intracellular ROS levels may result in activation of oncogenes, such as AKT, which are involved in cell proliferation, and inactivation of tumor suppressor genes, angiogenesis, and mitochondrial dysfunction, thereby serving as a signaling molecule in cancer survival. Conversely, when the level of ROS are further elevated, they can overcome the antioxidant defense systems of the cancer cells, causing cell death. It later says, consequently, there are two different approaches based on the redox balance to counteract cancer cells. In the first approach, oxidative stress can be decreased by scavenging our intracellular ROS. For example, increasing intake of antioxidants, vitamin C and E, can deplete oxidative stress, subsequently causing growth inhibition and increased susceptibility to cell death in cancer cells due to the crisis of energy production. However, this antioxidant supplementation reverse remains controversial. Increasing evidence has shown that antioxidant supplementation fails to provide cancer protection and can even affect cancer mortality, aka worsen cancer mortality and worsening disease. These observations are further supported and rationalized by recent studies demonstrating that oxidative stress can inhibit cancer progression and metastases, and that GSH and TRX antioxidant systems, which are under transcriptional regulation of NRF2, may promote tumorigenesis and resistance to therapy. So what I take from this is that because ROS is higher in cancer cells, there is a theory that if we were to give high amounts of antioxidants, vitamin C and E, we would deplete the oxidative stress, or we would decrease the amount of oxidative stress, and that would then cause growth arrest and potential of cell death. But when this is actually studied in humans, when they take vitamin C, E, CoQ10, other carotenoids, NAC, etc., that actually shows that in multiple cancer models, that cancer actually gets worse and death increases. So it is a theory that really doesn't pan out clinically. The second approach is by increasing ROS levels in cancer cells and therefore crossing the threshold of cancer cell death. This can be done either by direct production of ROS via exogenous, outside the body, approaches, or indirectly by increasing intracellular ROS concentrations via targeted inhibition of previously mentioned endogenous antioxidant systems in cancer cells. Several investigations are suggestive of the fact that the underlying mechanism of action and efficacy of conventional therapies, specifically radiation therapy and chemotherapy, inducing cancer cell death is the generation of elevated ROS levels during treatment. So radiation therapy is probably more classically associated with ROS induction. Some chemotherapies induce oxidative stress as well. And that explains why when you inhibit metabolic processes, specifically glucose and glutamine, which is critical for maintaining the cancer's not only energy, but also redox homeostasis, that would allow those therapies to work even better. And when there's high levels of antioxidants inside these cancer cells, it makes these cancer cells resistant to radiation therapy and chemotherapy as well. This is what I call the internal shield system of the cancer. Let's start out with looking at exogenous ROS generation. One mechanism of enhancing oxidative stress levels to target cancer cells is via exogenous delivery of ROS using different physical modalities. Ionizing radiation is widely used to treat many types of cancers. During radiation, cancer cells are eradicated through free radicals such as superoxide and hydroxyl radicals, which are generated by radiolysis of water in extracellular environments and indirectly damage critical targets such as DNA. In addition, radiotherapy can also alter mitochondrial membrane permeability and activate NADPH oxidase, which in turn further stimulates ROS production. Besides radiotherapy, other physical modalities that can induce a substantial increase in ROS levels are being investigated in cancer research, including photodynamic therapy, PDT, and cold atmospheric plasma, CAP. PDT is a light-based oncological intervention. Here, a photosensitizer is applied and subsequently activated by light. Upon activation, exogenously produced ROS is generated. CAP is an ionized gas that can be produced in atmospheric pressure near room temperature. It is composed of reactive oxygen and reactive nitrogen species, excited molecules, ions, electrons, and other physical factors such as electromagnetic fields and ultraviolet radiation. So this is the exogenous ROS inducers. Endogenous ROS generation. The second mechanism of enhancing oxidative stress levels is via intracellular ROS accumulation through chemotherapy or targeted inhibition of elevated antioxidant systems. A lot of chemotherapeutic agents enhance intracellular ROS levels and can alter the redox homeostasis of cancer cells. This amplification of ROS towards cytotoxic levels is one of the proposed mechanisms by which multiple chemotherapies induce tumor regression. The level of ROS generation is different among several compounds. Agents that generate high levels of ROS include the anthracyclines, doxorubicin, platinum coordination complexes, cisplatin, alkylating agents, cyclophosphamide, camptothectins, arsenic agents, and topoisomerase inhibitors, while nucleotide analogs, antifolates, taxanes, vinca alkaloids only generate low levels of ROS. There are two mechanisms for elevated ROS production during chemotherapy, namely through mitochondrial ROS or ROS generation and inhibition of the cellular antioxidant systems, and therefore interfering with ROS metabolism in cancer cells. Several agents, including arsenic trioxide, doxorubicin, and cisplatin, have been reported to induce loss of mitochondrial membrane potential and to inhibit respiratory complexes, leading to disruption of mitochondrial electron chain transfer and electron leakage, which is a major source of elevated ROS levels. So these are the endogenous or inside the body ROS inducers. And that would either be by increasing endogenously produced ROS or by inhibiting the antioxidant response elements and their subsequent antioxidants such as glutathione, thioredoxin, peroxyredoxin, catalase, etc. The other mechanism for intracellular ROS accumulation is the inhibition of the antioxidant systems during chemotherapy. For example, imexin, a small molecule used to treat advanced cancer of breast, lung, or prostate, binds to thiols such as glutathione, causing a depletion of cellular GSH and consequently an accumulation of oxidative stress in cancer cells. For some chemotherapies, more than one target site for ROS generation in cancer cells has been identified. For example, in addition to mitochondrial respiration, NADPH oxidase and thioredoxin system, TRXRs, are often other targets of arsenic trioxide-induced oxidative stress, inducing apoptosis. Besides chemotherapy, selective inhibitors that block components of the cellular antioxidant systems are being studied as anti-tumor agents that enhance endogenous ROS production. For instance, depletion of glutathione antioxidant system can also be achieved by targeting synthesis through buthionine sulfoxamine, BSO, which has been shown to exhibit anti-cancer activities in various types of cancer. Furthermore, inhibitors of the XC glycine glutamate antiport such as sulfasalazine and many others that we've seen on the channel, which have been substrate for glutathione synthesis. Another antioxidant is the thioredoxin reductase system, which has been shown to be upregulated in cancer cells and is correlated with cancer aggressiveness and drug resistance. TRXR is required to convert oxidized TRX to its functional reductive form, which can scavenge ROS. TRXR activity can effectively be blocked by the gold compound auranofin that is clinically used as an anti-rheumatic drug and functions as a thioredoxin inhibitor. In different cancer cells, it has been preclinically shown to induce ROS-mediated cell death, since the ROS scavenger, N-acetylcysteine, prevents its cytotoxic effects. So basically what they're doing is they're giving a drug this gold compound that inhibits the thyroredoxin antioxidant system. And they know that it's inducing ROS because when they give NAC, N-acetylcysteine, which is a glutathione precursor, it stops the cytotoxic effect or the cell death effect. This has led to the use of this oranofen in several clinical trials involving non-small cell lung cancer and ovarian cancer. The small molecule PX12 is another example of an antioxidant that inhibits TRX and is being used as therapy for advanced cancers in clinical trials. Conclusions. Preclinical studies have elicited that an increase in ROS concentrations through exogenous or endogenous ROS-inducing therapies, or a combination of both, can be an efficient anti-cancer strategy. Hence, the influence of these treatments on the TME should be considered. And importantly, both the immunostimulatory as well as the immunosuppressive effects have to be taken into account when investigating these anti-cancer modalities, because increasing ROS can be a double-edged sword with regards to immunomodulation, and the effects cannot be generalized over different treatment modalities. So this is our introduction into oxidative therapies for cancer. And after we hit some very key concepts, we're going to dive into specific oxidative therapies, and we're going to show how those work and then look at mechanism and outcome to see how they could be implemented into a holistic strategy for cancer, with ketogenic metabolic therapies being the foundation of that therapies to set these cancer cells up for maximum damage with these oxidative stressors and to protect the normal cells while these are going on. If you like videos like this, please like, share, and subscribe. Until next time.